it's time to discuss what is the result from the case 3, case 4, and case 5. Anyone wants to be a volunteer? For case 3, we start from case 3.
Can I, sir?
Oh yes, welcome.
Wait, let me.
Mikhail. Okay.
Let me have a photo first.
Yeah. Okay, you can share screen now. Yes.
I'm gonna take a picture first. Sorry, sir.
Take a picture.
Yeah, of the equation.
Oh yeah. Please.
Wait a minute.
Yeah, no problem. For the guest 4, maybe after Mikhail, who wants to try? Anybody wants to try after Mikhail for case 4? Nobody wants to try? So I have to choose. Maybe RD Hernando, are you ready for case 4? RD Hernando. Hello, RD.
Yes, sir. Hello.
Yeah. Are you ready for case 4?
I think I'm gonna try, but okay. Hopefully, I read the question correctly, sir, because
Okay.
I'm a bit confused.
Okay.
Okay, I'll try.
Okay, no problem. Let's
Okay,
try.
sir. Thank you.
Thank you, RD.
Thank you,
And
sir.
for the next is maybe Dava Raharjo. Are you ready, Dava?
Okay, sir.
Okay, thank you.
You're welcome, sir.
Okay, Mikhail, are you ready?
Okay, yeah, I'm ready.
Yeah, okay,
So,
good. Yes, perfect.
So from the what the equation you gave us, yeah.
Yeah.
Wait. Let me move this. From the equation that you gave us, this one, right?
Yeah.
I derived. Oh my god. Ntar ini nggak bisa okay. I derived to the graph. The first one is from the graph is like this, right? 0.1. Then from minus infinite to 32, the function is 0, so I write 0. And then from the 32 to 42, the function is 0.1, so I put fx as 0.1. And then from the 42, this is 42. 42 to the infinite, I put the fx as 0. So we get the equation is integral 32 to 42 x times 0.1. And then yeah, basically we integral it. This is supposed not to be any integral left because x per 10, the integral of x over 10 is x power 2 per 1 per half times x power 2 by 10. The equal is x power 2 per 20. This is what you get. And then I put the integral at 42 and 32, and I got 37 as the mean. Okay, sir, is it correct?
Oh yes, correct. Yes, 37, yeah.
37.
Okay.
And for the variance, the variance, I use the same, but this time I skip the what getting from the this equation. I instantly go to integral of 32 to 42 and put the x and the fx, and then yeah, because this is x minus 37 over 10 or 2. The integral of this is x negative 37 power 3 over 30. And then this. And then I put the 42 and 32 into the equation, and I get the total is 250 over 30, in which I get 8.3. Is it correct, sir? Or haven't I done the what? Or should I get the root of 83, 8.3?
Okay, later I will check. Wait
okay,
moment.
okay.
Actually is minus. Okay. And yeah, 8.3. Okay, it's correct.
Yes. Okay.
8.33. Yes, yes. Perfect.
Okay, thank you, sir.
Congratulations. Okay, anyway, please keep it
Okay.
this screen on. So I want to make a bit how to say
Annotations?
explanation, yeah, annotation.
Should I delete the
No problem.
Okay.
Okay, the thing that I want to point out that first is the okay, the mean of uniform distribution. You can see it's simply, you can see the result is 37, right? 37 is really on the middle, yeah. Okay, it's correct, yeah. And you already know that for the mean and for the uniform, actually this is kind of uniform distribution, yeah. Uniform distribution. Uniform, why we call as a uniform? Because uniform, it's mean the equal probability along the sample size, along the spectrum, you know, from 32 until 42. Yeah, the probability of occurrence is same. It is 0.1. So that's why this is the uniform distributions. And in general, how to compute the mean is like this. Yes. And then by this, and we can see that the mean is really located in the center of sample size. Yes. Okay. And for the variance, we have yeah, this correct, is absolutely correct how to compute this, but there is another way, which is the variance for uniform distribution is simply by the b minus a powered by 2. B is the maximum range here, and the a is 32, and the result will be equal to the 8.33. That's correct. Okay, this is just another way instead of computing the integration. Actually, this formula is computed from the integration actually. Yes, thank you, Mikhail.
Yes, sir.
Yes, now you can stop screen. Okay. Okay, the next is I forgot RD. Yeah, RD.
Yes, sir. Okay.
Yes, please try for the case 4.
Okay.
Yeah.
But sir, I actually can you see the screen?
Yeah.
Wait, oops. I'm a little bit confused about the fx. Is it correct? 1 per the root of 2 pi to the power of e to the power of negative x squared per 2?
Which one?
The fx.
Fx, yeah. Fx already written, right?
Yes, but I don't know. I'm afraid I read the powers wrong because
Yeah. This
yeah.
core, what do you mean? The location for A is belong to what?
Is it to the power of pangkat of the 2 pi?
No.
No. Oh, okay. Then I read it wrong, sir, because I'm a bit confused with that.
Okay. It should be something like that. Wait a moment. Okay. It should be 2 pi E minus
Oh, okay.
X 2, or equally E minus X by 2 per 2 divided by 2 pi.
Oh, okay. I think, well, I guess I'm wrong, sir.
Okay.
Yes.
Can you try a letter? Maybe I will skip you and then we move
Okay.
forward to the Dava.
Okay, sir.
Dava. The next is Dava, right?
Wait, sir. Okay.
Okay.
Wait, sir.
Yeah.
Let me. Okay, sir.
Yeah.
The first thing is mean. So the formula is mu x equals to the integer of minus infinity. And I haven't finished the equation, sir.
Yeah, no
So
problem.
I think
You can
Okay.
you can conduct through this screen. Yeah.
okay, sir. X is 5 squared per 4. Yeah. And then
Are you sure for?
and then
It should be 2.
oh, it's 2. It's 2 then. Sorry, sir. It's 2, and then we can make the equation to be like this. X e e L, and then we're gonna Wait, sir.
Yeah, yeah.
Mm. Sir, if I have a mistake, just please tell me,
Yeah,
sir.
yeah, yeah.
I'm afraid
Yeah,
that okay.
yeah, of course. Sure.
Sir,
Yes.
is it pangkat 2-nya ini nggak ke semuanya, sir ya? Wait, I think, oh no. Tadi saya mangkatin ini dua-duanya jadi per 4, sir. Astaga.
Okay. Okay. Yeah, it seems that yeah, that is a wrong from the beginning. But
Oh my god.
okay, anyway,
Sorry, sir.
no problem. Yeah. So since you don't have the result, maybe. Okay. Yeah, the things that Dava actually the step is correct. Yeah, the step is correct. I follow your explanation. The step is correct. Yeah, but I don't want to check more detail about how to integrate because this is not calculus course. Okay. Anyway, okay. Maybe the solution is yeah. From your point, from your result, the way of compute is correct. Means that how to integrate and something and so on and so on. Even is not get the result yet, but the things is that I want to point out. It is from the graph. From the graph, you see that if you're familiar with, actually this graph is what we can call the name. What you can call the name of the graph. Dava? Hello, Dava?
Yes, sir.
Yeah. Can you call the name this graph?
Is it the like this probability distribution?
Yes, it is correct. But with this form, it has a specific name. Actually, this is a probability distribution graph or distribution functions. But if you look at this pattern, we can call as a Gaussian.
Gosh.
Gaussian distributions. And the Gaussian distribution
Inverse quadratic.
not universal. You're not uniform. This is a Gaussian. Let me show you something. Can I share screen with you, with all of you?
Okay, wait.
Okay. And I can simply by search from the internet, from Wikipedia actually. Sorry for the search. Actually, it's correct. This is normal distributions and also well known as a Gaussian distributions. Gaussian distribution, what is the form of Gaussian distribution is, this is likely something like this.
Density.
Yeah, the probability density function, the probability distribution function, we can call it is the same. Yeah, you can see it's like a bell shape, bell shapes with the negative infinity at the left side and positive infinity at the right side, For example, pick up the green one here, this one. This is a positive infinity and this is negative infinity. This is a positive infinity. And you know, this is the expression, mathematical expression of these functions. It's really same with the case 3 and case case 4 and case 5. Okay, let's go back to our case. Stop share, and then I want to share this one. Okay, you can see here, this is kind of name, we can have name as Gaussian distributions. Can you see? Yeah, everybody can see my screen.
Yes, sir.
Yes, sir.
Okay.
Yes, sir. Yes, sir.
Okay, yeah, you can see here the original function is fx 1 delete 1 square p sigma a minus x minus mu power by 2 sigma power by 2. Okay, you can see here from this expression the sigma is from this one, the sigma is, can anybody can answer? Sigma is equal to
Sir, I cannot see your pointer, sir.
huh?
Pointer.
Your mouse cannot be seen.
Your sharing screen is paused. Oh, wait a moment. Okay, right now is okay. Can you see?
Sir.
Can you see the sigma
Yes, sir.
here?
Yes, sir.
Yes.
Yes.
Yeah, you see, this is the original case, and this is the function of Gaussian or normal distribution. You can see. So best look at these two functions, you can determine the sigma equal to
Plus minus 1.
equal to
Positive 1.
sigma is
1,
for?
sir.
1. Okay, correct. Yeah, correct. Yeah, sigma is 1. So also we can determine from this, sigma is correct. Sigma is 1. How about the mu?
0, sir.
0, sir.
0. Okay. Okay, mu is 0, sigma is 1. From the graph, you can see the mu, we can determine, or we can see from the graph, actually the mu is here. Okay. How about the sigma? Sigma from the graph, we cannot determine where is the sigma. Actually, sigma, we only can know, we can only know by computing. Yeah, compute using integrations. For the mu, we can see from the graph, actually at the center. Yeah, so the mu is 0, this is mu is 1. But from given, if you can see the formula, the function, and you can determine both. But from the graph, you can only determine the mean. Okay. From the same case here, so we can easily see that mean is 5. Is it correct?
Yes, sir.
Yes. For the variant is 1. Yes. Yeah, you can actually how to compute. Yes, it's based on the formula at the previous slide. Yeah, this one. This is how to compute. No. Actually, we are dealing with the continuous random variable. Yes. Okay. This is mathematically you can compute this. Yeah, mathematically you can compute using this formula. And I understand that the computing mean and the variance based on this formula, particularly if we have a complex function, something like this, is a bit difficult. I mean, challenging, takes time as well. Yes, I understand that. But if you are interested in, you can prove by yourself that by integrating, this one is correct. Of course, don't worry and don't be worried that maybe at the exercise or in assignment, I will consider the problem actually. Yeah, integration is such thing, computing the mean or variance using the integration with the complex function takes time, of course. But at least you already understand how to compute formally using integrations. Okay, any questions? Oh, maybe one question. If you have this probability distribution, what is type of this probability distribution graph? Is it continuous random variable or discrete random variable?
Continuous.
Mikhail, continuous. Any other opinion?
Is it continuous?
Continuous? Dava continuous?
Is it
Are you sure? Maybe Dava, why you say that this is continuous?
because it's constant?
Because it's constant.
The graph.
The graph is constant. You mean this one?
Yes.
Constant. Okay. Mikhail. Okay. Thank you, Dava. How about you? What is the reason why you say continuous?
The probability distribution from the point 32 and 42 is always 0.1. So if discrete, that means that there's no in between 32 and 42. But in this graph, it shows that in between 32 and 42, there's also the probability of 0.1. That's my answer, sir.
Yeah. Thank you, Mikhail. It's almost correct. Dava is also almost correct, but not perfectly. Any other questions? And any another sample? Yeah, this is a continuous random variable. I mean, yeah, this is continuous random variable, and the consequence of it is resulting the continuous probability distribution. But the reason why?
Sir.
Yes.
Is it because there's an infinite amount of numbers between 32 and 42? So that's why it's continuous.
Okay. That's the point. Infinite number, it means that from this point to this point is really continuous. There is no discrete. Yeah, maybe some of you are already correct, but the word of continuity, you should mention it. Because this is continuous, there is no discrete. Even though in here is 0. But this is really continuous. It means that in every single point, maybe let's say 22.9999, there is always a value. Always a value. Okay, yeah. I hope everybody understand. Okay. Anyway, any question until this slide? Case 3, case 4, case 5. Any questions? Any problem computing this mean, variance, and also linear combinations? The concept, yeah, of them. Any questions? Three, two, one. Oh, okay. No questions. Okay. The latest to slate we have a Jbc Theorem, yeah, actually, and then also we have to slide more. Please, I need your attention, maybe 5 minutes or 10 minutes. Okay, I will explain about the Jbc Theorem. Okay, actually, Jbc Theorem is nothing, but the Jbc is a Russian person that realize the behavior of probability distributions. It deals or it works from for continuous and discrete case. Okay, let's take a look. Before we talking about the Jbc Theorem, we have to really understand about this one. Tell the meaning of variance. Actually, you already know the variance, or standard deviation is another word of variance. Yeah, of a random variable. You know that the variance can be small and can be large. Is it correct? Okay. What is the meaning of small variance? Maybe Edro, can you explain what is the meaning of small variance in random variables? Edro, are you there?
Yes, sir. Small variance. Small. Did you just say small variance?
Yeah, small variance. What does it mean?
I'm not sure, sir. Is it something that is close to a certain value?
Close certain value. What a value?
The average, sir.
The average. How do you know that?
I don't know. I think it would be some memory, sir. Small variance, right?
Yeah, formally is correct, but I need your is that really, by your definition, is that really you already understand what you mean, what you said?
I'm familiar that the difference between small and large variances is the distance of them to the mean, sir. That's the only thing I'm familiar with.
Okay, are you sure? Not sure.
Yeah, not really sure, sir.
Not really. Okay. Yeah. Formally, yes, correct. It is correct. Yeah. Actually, the variance formally defined that is how far some number relative to the means.
Oh, sir. Is it the how spread out the data is?
Yeah, it is another way. For example.
So if small variance means more data is collected near the average, while if large variance means it's more spread out.
Yeah,
am I correct?
It is more clear explanation. Okay, thank you, Edro. Yeah, seems that the definition from Edro is correct, but you can see from the two graph here, is really sharp and this is less sharp. Less sharp means that the data is spread out. To the left and the right. It means that the data is more, it has a larger variance, is more varies, ya. Datanya itu lebih bervariasi. Perbedaan antara itunya apa? Antara outcome-nya itu lebih banyak. Ya ketika sebagai contoh, ketika apa namanya? Ketika kita misal mengambil data tinggi badan lah ya, sebagai gampangannya. Anda mengambil tinggi badan orang Indonesia. Orang Indonesia itu akan rata-ratanya mungkin saya nggak tahu, saya nebak saja ya, misalkan 165. Apa namanya, paling tinggi mungkin 173. Di sini paling rendah mungkin sekitar 155 misalkan ya. Ini data kalau kita ngambil orang Indonesia. Coba kalau kita ngambil orang dunia. Orang dunia. Jadi orang dunia. Mungkin batas bawahnya tidak di 155. Tapi mungkin di 140-an. Mungkin ya. Dan batas atasnya tidak di 173. Tapi mungkin bisa sampai dengan 200. Artinya, dilihat dari ini spektrumnya, lebar spektrumnya atau lebar sampel size-nya itu lebih besar. Ketika lebih besar, maka grafiknya lebih landai. Lebih landai artinya lebih bervariasi secara matematis. Mathematically, we can say as more variance. The variance is larger compared to the only Indonesian people. So that's why when we have a sharper probability distribution, it means that the variance, let's say this is the variant 2 and this is the variance 1. The variance 1 it should be larger than variant 2 mathematically. Yes. Okay, is it can be understand, yeah? And keep in mind that the area under the graph, yeah, the area under the graph here compared to the graph here, even the more spread, or this is a sharper, the area is same, equal to 1, right? Because the area under the graph in probability distribution graph is always 1. Integration from minus infinity to positive infinity. Yes, it is correct. Okay. From this preliminary, is there any questions? No. No. Okay. Please focus on this in this graph. Actually, the basic understanding we can use that. And for the case 1, standard deviation. Please look at this graph which says standard deviation 1. Please don't be confused. We say standard deviation because the standard deviation is just square of variance, so it's proportional. Okay. Standard deviation 1, you can see this is the graph, standard deviation 1. And compared to the standard deviation 2, is more, how to say, less sharp, ya, less sharp, lebih landai, lebih menyebar, begitu ya. You can see here, ini yang 1, ini yang 2. Oke. Oke. Saya fokus ke yang ini, kemudian saya ingin then I want to annotate and make some, how to say, make some area here. I draw some area here, yeah. Draw some area. Okay. This area, this blue area, so that's, then we can say a probability blue area. It is corresponding to this one. Okay, is correct. And then this area is limited by minus k until k. Okay, from this point can be understand, yeah. Okay, and then from the graph standard deviation 2, also I want to make a area as well. The area should be something like this. And then something like this. And then I make this one probability of yellow. Yeah. And then if I want to keep that this area should be equal, the area for the blue one, the blue area and yellow area is equal, the size, it can be easy that the number of L, let's say this is minus L, this is a positive L, let's say L. You can see, focus on this one, the L is greater than K. Can you understand? Can you agree? Do you agree with this?
Yes, sir.
Okay. And then this relation, it means that the L should be greater than K. It's really related to the nominal of standard deviations or nominal of variance. So that's why in this case, since the L greater than K, also we can look at back that the standard deviation 2 is greater than standard deviation 1. Actually, it's not correct. Nah, something like that. Sorry. I have to change this one. Something like that. So it is proportional. You can see here that the L is getting larger, and when the standard deviation is larger, and we have to keep that the size under the graph is equal. Okay, from this point. Okay, based on this definition, based on this understanding, we arrive at the Jbc theorem. Okay, I have to make it clear. Wait a moment. Okay, you can see back to this graph. Actually, this is a limit. This is a limit. This limit corresponds to the mu minus K standard deviations, and this is the mean. This is mean plus K plus standard deviation. This is the, let's take, for example, this is a Gaussian, but actually this is not all, not should be Gaussian. It means that this probability can be any, it works for any probability distributions, including continue and discrete. Okay. So given this limit, we can write that probability given size of under the graph, this is yellow one. Actually, this is the probability of yellow. Yeah, it is can be formulated as 1 minus 1 divided K by K power by 2. Yeah. Okay. So we can arrive at the conclusion that given any probability distribution with mean and the standard deviation, then the area between this point and this point has size greater than this point, this formula. With K is any number. Okay, yeah. Please, how to say, look at this slide and maybe text maybe relax to understanding this formula. Okay. Is there any question? Maybe you have questions.